This reference design is for making a voltage measuring product. It includes everything from schematics to assembly instructions and behavior control.
Rollout. We share hardware reference designs for robotics so you can make your own hardware.
Hi, welcome to Rollout. I'm Jeremy, and today we're rolling out the E-28 Voltmeter. The voltmeter is a great tool for troubleshooting and debugging. It gives you a visual output of your voltage coming in, and you can graph that using the ADC graph in EasyBuilder or Graphy, a plugin that can be added to EasyBuilder. You can also do voltage logging, going to your favorite spreadsheet program. You can do battery monitoring with it, as well as it works as a low-budget oscilloscope, and you can kind of see how clean your signal is with that. And it's multi-platform, so it works for whatever microcontroller board you want to use it with. It has the classic GVS standard, ground voltage and signal. All right, let's hook up the E-28 voltmeter. First, we're going to need a JST cable. So this has a JST PH 2mm pitch connector on one side and a DuPont 3-position GVS style connector on the other side. So that's ground voltage signal. Connect that up. Next, we'll need an EasyBuilder compatible board. We're using the IO-Tiny today from EasyRobot. Connect that up. And so we're going to want to connect to one of the ADC ports here. So we'll connect up there, and the LED tells us that we have correct polarity connected. So this board actually has reverse polarity protection. I'll just show you. You can plug it in the other way, and it's still okay. Next, we'll connect a variable voltage supply, and that'll give us our the voltage we need to measure here. So we'll connect black to black, red to red. Next, let's connect to EasyBuilder. Find our IO-Tiny there, connect up. Just give it a few seconds to connect. There we go. Okay, we'll add some controls here. We'll go under ADC, and grab ADC value. And this, you can see the value that's coming through. And so this value doesn't correspond directly to the value we're seeing here, 15.1. So what we're going to do is we're going to adjust this into the middle, because the middle is a good place to calibrate this. I'm going to go down to a value of 127 in the software there. So 127 is half of, well, close to half of 256. And that's the maximum ADC values that we'll get is 0 to 255, so 256 values. So that's close enough. So we'll do a calculation here. We'll go, so it's 8.9 volts. Let's get our calculator out. 8.9 volts divided by 127. Let's do 127. So that gives us basically 0.70078. Let's copy that. And we're going to adjust the settings here for that and change the multiplier. Save that, and that should give us our 8.9. There we go. So perfect. Next, we're going to add the ADC graph. So this will show us kind of a pictorial view of the signal coming in. It's kind of like a low budget oscilloscope. It gives us how clean our signal is, but also gives us the transitions. So if you slowed your code down to be pretty slow, this could pick up exactly what transitions are happening. And so I'll show you like an adjustment of voltage, and you can see that adjusting on the graph. We're dipping lower here. There we go. Let's add graphy to our program. So go into graphs, graphy. In order to use graphy, you'll actually have to write an easy script, but it's pretty simple. Just go to scripting, easy script. We'll get into the scripting here. Let's add a loop. Can't forget the colons up here. Next, we'll have a variable x equals get ADC 0. That's the ADC that we are on. And then we'll go over to our cheat sheet, go down to graphy, we'll add data. So let's change the series name here to ADC value. And let's change that data to x. And we'll also need a sleep function. So this isn't grabbing the data really quick. Okay, we'll save that. And now let's run it. There we go. We can see our voltage being graphed. We can adjust it with my screwdriver here. See it going higher. And graphy adjusts for that. Changes the scale. And then we'll stop. So one neat thing you can do with graphy is actually log the output values by saving to a CSV. One thing to note is that the voltage isn't perfect on the maximum and the minimum because of the voltage protection diode that's on the circuit here. So there's a voltage protection diode and then the voltage divider, and we'll get into that when we talk about the schematic. So here's the schematic. As you'll see, these are the inputs, the ground side and the signal side. And next we have the polarity protection diode, just in case you hook up your wires backwards on the voltage source. Then next we have the voltage divider, and then that goes to the ADC pin on the output right here. So this circuit allows an input of 17.5 volts in order to output a 3.3 volt output signal. You want that to be a maximum of 3.3 volts so it doesn't damage the ADC pin. And this circuit doesn't measure negative voltages. Just be aware of that. Here's the bill of materials. It shows the voltmeter board, the PCB. We have our resistors, and then we have the reverse polarity blocking diode, set of multimeter probes, and the LED, and the JST pH header. So the last portion is the rubber feet, which is optional. It just allows the board to be isolated from the surface that it's on. These are the electronic assembly notes. It shows you how to assemble this board. Starts off with a list of tools and supplies that you'll need. Next, it shows you that the diode has to be in a certain orientation on the board. Make note of that. Next, it shows cutting off the plugs off the multimeter leads, stripping those back, putting them into the board, and solder them to the board. And it just shows you just to clean up those two solder joints that you make. And then pull those leads tight. And then, like I said, optionally add those rubber feet onto that board. And that's that. One last thing I wanted to point out is that you don't have to solder these multimeter leads directly to this board. You can actually use banana jacks because there's a layout pattern for these. I didn't do that because I wanted to have a solid connection from the leads to the board. And sometimes when you buy these jacks, they don't ultimately mate with the plug perfectly, so they can pop out. You'd have to do some testing. So this is what it would look like with the jacks on board. And you can also add mounting holes. I didn't add any mounting holes here just because I wanted to keep it nice and small, but you're definitely welcome to change the design and add what you want on there. So that was the E-28 Voltmeter reference design. Find the links for the Synthiam behavior controls and the GitHub reference design files in the description box below. And don't forget to subscribe so you can be notified on the next rollout videos. See you later.
Thank you for watching Rollout. For more information, visit www.synthiam.com.